Hey everyone, and welcome back. All right, today we're jumping into one of the smartest strategies for handling infinite series: comparison. I mean, what do you do when a series looks almost like one you know, but not quite? You compare it. Think of it like a tale of two tests, two awesome tools that are going to let you solve a whole new class of problems. So let's get into it. So check this out. On the left, you've got a classic geometric series. We know it converges, easy peasy. But on the right, all we did was add a +2 in the denominator. That's literally it. But that one tiny change means our geometric series test just doesn't apply anymore. So what now? How are we supposed to figure out if this new, messier series converges or diverges? And that right there, that's the whole issue. You see, a lot of the tests we rely on, they need the series to be in a very specific, clean format. Even the smallest change, like that little +2, can make a test completely useless. This is exactly why we need a new way of thinking, one that's built more on logic and intuition. Okay, so let's bring out our first tool, the direct comparison test. I kind of think of this as the common sense test, because honestly, the logic behind it is just so intuitive. It's all about finding a series you already know and then using its size to figure out your new one. Okay, so here's the first part of the logic, and it's super intuitive. Imagine you've got a series, and you know its sum is a finite number, right? It converges. Think of that sum as a hard ceiling. Now, if you have another series where every single term is smaller, well, it's trapped underneath that ceiling. If the bigger one can't get to infinity, there's no way the smaller one can. It's stuck. It has to converge too. And believe it or not, the exact same logic works in reverse for divergence. Let's say you have a series that you know just shoots off to infinity. It diverges. Picture a rocket ship taking off. Now, if your new series has terms that are always bigger, it's like it's sitting on top of that rocket. The smaller one is already going to infinity. The bigger one is definitely getting a free ride straight to infinity. It's got to diverge. All right, so let's put this into practice with that first problem we saw. We're going to compare our messy series to that simple geometric series, 1 over 3 to the n. The whole game here is proving that our series is always smaller, and since we know that bigger series converges, it has that ceiling, our smaller one is trapped, which means it has to converge too. Simple as that. So yeah, the direct comparison test is awesome when it works. But, and this is a big but, it's got a major weak spot. The whole thing depends on you being able to set up that perfect inequality, and sometimes you just can't. And this is the question that trips everybody up. What if you were looking at something like, say, 1 over 3 to the n minus 2? Now the denominator is smaller, which makes the whole fraction bigger. Our inequality is completely flipped. The test doesn't tell us anything. And just like that, our simple, intuitive tool just hit a wall. And you're gonna run into this a lot. You can just look at a series and your gut tells you, hey, this should behave just like that other one, but you just can't get that inequality to work. This is the moment where we need something with a little more muscle. Well, this is where we bring in the big guns. Meet our second tool, the limit comparison test. This is the power tool of our little toolkit. It totally gets around that tricky inequality problem by looking at the whole situation in a completely different and usually much easier way. So instead of that tricky term-by-term size comparison, this test looks at the big picture. It's all about their long-term behavior. You take the terms of your messy series and divide them by the terms of a simple series you know. Then you see what that fraction does as n shoots off to infinity. Basically, we're asking, are these two series growing at pretty much the same rate way out there? And everything hinges on the answer to that limit, which we'll just call L. If that L is any real positive number, not 0, not infinity, then boom, the two series are locked together. They share the exact same fate. Either they both converge or they both diverge. It's an incredibly powerful shortcut. So when is this thing your go-to? Well, it is an absolute lifesaver for those messy algebraic series. You know, the ones with polynomials and square roots and all sorts of stuff going on. That's where this test really comes into its own. But how do you pick the right series to compare it to? Now, this next part is maybe the most important trick you'll learn for this test. It's a total game changer. When you need to pick your comparison series, just look at your messy one and ignore everything except the highest power of n on the top and the highest power on the bottom. Everything else, all those other little terms, in the long run, they're just noise. They don't matter. Okay, let's take this strategy for a spin with the general harmonic series. Using our highest powers trick, the only thing that matters is the n on the bottom, so we compare it to the simple series 1 over n. We do the math, compute the limit of the ratio, and we get a positive, finite number. That number tells us they're linked, they have the same fate, and since we know for a fact that 1 over n diverges, our series has to diverge too. How easy was that? Fantastic. Okay, so we've got two amazing tools in our belt now. The simple, intuitive direct comparison and the powerful algebraic limit comparison. The last piece of the puzzle, the real pro move, is knowing which tool to grab for which job. And this little cheat sheet here just lays it all out. If you look at a problem and a simple inequality just jumps out at you, go for direct comparison. It's fast, it's clean, but for pretty much everything else, especially those messy algebraic series, just go straight for the limit comparison test. Its big idea is so powerful. If two series basically act the same in the long run, then they are the same when it comes to convergence or divergence. So what's the big picture here? What do you really need to remember? 1, always try the simplest tool first. If the inequality is weird or goes the wrong way, don't waste time, just switch gears to the limit comparison test. 3, always remember that highest powers trick for picking your series. And 4, and this is the most important part, the goal here isn't to just memorize a bunch of rules. It's about building a toolkit so you can walk up to any problem and know you have a way to tackle it. So I'm going to leave you with this one thought. Now that you have these two tests, a complicated-looking series isn't just a hard problem anymore. It's a puzzle. And the cool thing is, you now have the two keys that can unlock it. The only real question is, which one are you going to try first?